Good evening. Welcome to Kopernik Observatory. It's great to see a bunch of new faces in here. My name is Drew Desker. I'm the director here at Kopernik. And you guys came up on a great night. We're going to have an opportunity to learn about what's up in the skies, and you're going to be able to go outside and actually look at what's up in the skies tonight. So just a matter of interest, who's here for the first time or hasn't been here since their 4th grade field trip? All right, good portion of you. All right. Who here are members? Oh, just a couple. All right. Well, the people who raised their hands second, the members actually have a very special knowledge, a superpower, I'd almost call it. A Kopernik membership gets you into Kopernik on any Friday nights that we're offering a program, and some special events as well. Those members came up for the eclipse that they didn't get to see. but the other thing is that we belong to what's called the ASTC, the Association of Science and Technology Centers, and it's a consortium of 380 plus science centers that honor each other's memberships. So with the Kopernik card, you could go into the Robeson Museum, you could go to the Museum of Science and Technology up in Syracuse, or the Franklin Institute down in Philly, or the Intrepid down in New York City that actually has a space shuttle down there and a Concorde. So if you sort of like this kind of place, the Kopernik membership is actually a pretty good deal. In fact, a few years ago, I took my daughter down to the Franklin Institute, and for the cost of my ticket and her ticket, it would have been actually more expensive than a full year's membership, family membership. So if you like this kind of place, consider supporting us with a membership. Up on the screen here, we have our website, and we always keep that up to date with what's going on. So tonight, we actually, is our Summer Skies program. But also tonight is actually this weekend sort of closes out our registration for our Rocket Fest. So this is an opportunity for families to build those Estes rockets. And if you haven't registered already, you can actually register tonight and actually pick up your rocket tonight. And then next Saturday, we have our, at this point, I think we've got like 108 registered rockets that will be launching from here. And so if that seems interesting to you, you can build it at home, and then you bring it up here during your launch window, and then you or your child gets to hit the button that sends it skyward. Also, our summer camps registration have been very, very popular. A number of the camps have already sort of filled up, but we still have some openings in some of our camps. And among the camps, one of the camps that I run is called Welcome Aboard the International Space Station. It's for rising 4th and 5th grade students. And during that time, during that week, the students will learn what kind of training astronauts go through, what kind of work they do on the International Space Station. We talk about satellite orbits and radio communication, and we actually have an arrangement with NASA where our students will actually get a chance to ask a question of an astronaut that's actually on the International Space Station as they're flying by. We have a ham radio station here that is able to communicate directly to the ham radio station on the ISS. So we do some fun things up here. So if you've got a child or grandchild or somebody you think that might find a hands-on STEM summer camp, check us out. What else have we got going on? What else do we need to talk about? Oh yes. So back in March of 2020, again, we would always have our Friday night programs, but then COVID hit, and so we couldn't continue to gather here in person. So I said, okay, fine, we'll just pause these Friday night programs for a couple of weeks until this COVID thing blows over, and didn't exactly work out that way. So what we decided to do is, look, we had all these speakers lined up. Why don't we have them just zoom into our facility here? We then turn it back around and push it out on our YouTube channel. And we do, in fact, have a YouTube channel which now has over 13,000 subscribers. Again, the upcoming programs, or tonight's is the Summer Skies. Next week is a program on science and religion. But what's also great about this is you can actually go back to our previous. Last week we had a talk on dinosaur artifacts. The week before that, ring worlds. Saturn is not the only planet in our solar system that has rings. But not everything we do is always about astronomy. We actually had a Binghamton University professor and his grad student show off their robotic seeing eye dog up here. But then the week after that, we actually had some high school students talk about their competition robot. So even if you don't get a chance to come up on a Friday night, you can watch us on our live stream, and we have people watching on the live stream right now, or you can watch it at your convenience. And what's been fun, actually, is as we were doing these live streams, people started, coming often, again and again. And then when we finally able to reopen the facility, we actually got to meet the people that we were just seeing on, on YouTube on the chat. And but we literally have people from around the world that will be watching. So anyway, our YouTube channel has been very popular, and it definitely is. It's great that you can always go back and check out some of the previous talks that we've had. So again, Friday nights are really an opportunity for us to do we call it continuing education or lifelong learning. Yes, we do a lot of work for young students, getting them hopefully interested in pursuing a STEM career, but we really try to make this something where we could all learn something. I keep saying, I wish I could live another 100 years, because the technology and science keeps just progressing so much. I'd love to see what's going to happen in the next 20, 30, 40, 50 years. See where we are. Back when I was growing up, when I was your age, I used to, my parents would have me walk to the TV to change the channel. Now what? and also the TV stopped at midnight. So, but anyway, tonight we have an opportunity to learn about what's coming up in the summer skies, and this will be something that you can then take home with you and use this whole summer. So we're very fortunate to have on our staff Jenny Cardy. We call her our live stream astronomer, and I think, Jenny, we're just going to pass it right on to you.
Turn my mic on, and we'll switch on over to our slides and make sure this is full screen. Okay, yes, topic tonight is summer skies, and I'm sure there's been a case where I've run a skies program and the skies were actually clear afterwards in the past, but most of the time it's not the case. And I'm excited tonight that we'll be able to send you out to the telescopes with those clear skies. And we have some exciting things to look at tonight, which we'll get into. This is not just there's like some overlap between, we're in late spring now, and we're heading towards summer. So there's going to be some overlap with that. But we're also going to focus on, throughout summer, what can we see? Things are going to change a little bit as we go from June to mid-September. Okay, so this is actually an image of something that you can see in the summertime, which is the Milky Way galaxy, at least the core of the Milky Way. We'll get into exactly what you're seeing there when we come to that section, but that's a little preview on the Milky Way. Let me try my clicker here. And maybe it's not going to work. Come on. Okay, we'll use the mouse. So what are we going to look at tonight? I'm glad I saw some new hands out, new visitors out there in the audience today, because part of this presentation is the ABCs of stargazing. And for those that have been to our skies presentations before, I apologize for the repetition. But it is important that we kind of set the scene for those unfamiliar with the sky, so we can give you an idea of how astronomers navigate it and how you can start to as well. So we'll go through those ABCs, and then we got what we can see in the sky. So we'll talk about the ISS and what that even is, SpaceX Starlink, solar system objects, the Milky Way, and deep sky objects. That's an overview of really what's out there, items that you can see with your eyes and also with telescopes. And then finally, we'll wrap up with some observing tools that you can use that are really accessible. Okay. So the ABCs of stargazing. A is for angular size and distance. And this is how we can measure the distance between objects, or even start to think about how we can bring coordinates into the mix and pinpoint where these objects are. Spoilers, that's what the C is for, is coordinates. So this very much ties into that. So you have a handy tool to measure objects in the sky. You can just use your hand. Now, what's important with this is that you have your arm all the way extended. Okay, so let's try that first one. We're measuring in degrees. That's an angular distance. So think of if you've used a protractor before to measure an angle, that's what we're talking about here. So 1 degree, it's that 1 degree extended out. So the space between those lines gets wider, right, as that angle goes out. So 1 degree, we can raise our arm up and imagine looking out in the sky. If we want to imagine the moon, we can do that. The moon will rise later tonight. The width of your pinky at arm's length is 1 degree across in the sky. The moon, and incidentally the sun as well, is about half that size. It's about the size of your pinky now. So about half a degree for those objects in the sky, which may sound pretty small. But certainly when we're looking up in the sky at these celestial objects, those are going to be the 2 biggest ones. Now, with the moon, of course, you can look at that safely. The sun, as you may have learned from the solar eclipse, or not maybe given the clouds, you need solar eclipse glasses or solar glasses to observe that safely. So don't stare at the sun. But they are about the same size in the sky. Then we can do 3 fingers out, arm's length, and that's 5 degrees across. Then we can make a fist like this, arm's length, 10 degrees across. And then your pinky finger and your index finger, and you can spread them out a little bit. And that's 15 degrees across in the sky. So we could even try this tonight with the Big Dipper. We'll go on a star tour where we can point out these objects to you in the sky, and we'll point out the Big Dipper. And you can try and take what you've learned. If you even want to just snap a picture of this quick with your phone, you can do that. So you can take that outside with you and practice measuring these, not just the Big Dipper, but other objects too. The distance between stars, distance between the moon and constellations. There's lots you can do with this. So you can see if you're looking at this orientation of the Big Dipper, the cup itself is about 5 degrees in height. So you can try and measure that. 5 degrees on just about either side. And then the width of the cup is about 10 degrees. So that would be about a fist across. So yeah, use that handy trick to measure objects in the sky. It's a really useful, I'll try and limit my use of handy. It's a really useful tool to also inform people of where objects are and how big they are. Trying to explain constellations in the sky when you're just using, like your pointer finger, for instance, pointing things out from your own perspective really does not do a lot for the person standing right next to you, because they're shifted and your finger is pointing to something else for them. So doing your best to give people a sense of scale, how big is that constellation in the sky, it's all very valuable. So this is a great starting point, is your angular distance measurements. Okay, and how about B is for brightness. Now in astronomy we call this magnitude. And here's a diagram explaining magnitude. And right off the bat, I will tell you, it's not going to be intuitive at all. So let's just start right in the center. Like, when you're dealing with a line graph like this, great to start at the 0 point, right? Okay, so we'll start there. What's our 0 point for brightness? It's down here. This is the star Vega, which is a reasonably bright star, a good summer star as well, part of the constellation Lyra, but not the brightest star in the sky, not the brightest object in the sky. So let me ask you, what is the brightest object in the sky? Yeah, the sun. The sun's going to be the brightest, so bright that we shouldn't look at it. And you can see the sun is on the left-hand side of our number line in the negatives, pushing -30 in magnitude. Okay, say it similar here. Next brightest object in our skies is the full moon. There's the full moon there. You can see the moon in the daytime, really bright at night. Last night was the full moon. Tonight's going to be basically a full moon as well. With the darkened sky around it, it's almost overwhelmingly bright, but safe to look at. But again, on this negative side of the chart, one of the brightest planets in the sky, Jupiter, again in the negatives. And then you flip over to the other side with the positive numbers, where all the dimmer objects live. Objects like the Andromeda galaxy, which is around 3.5 in magnitude. Out here, this is labeled around 6. That's the faintest naked eye object that your eyes can see. Now, what does that mean? It means you don't have any telescopes, no binoculars. You're just looking up in the sky, and around magnitude 6, that's the limit of your eyes, of the human eye. Beyond that, you need equipment to start seeing objects further away, be that telescopes, binoculars, cameras. You can do a lot more with those than that human eye can on its own. So something beyond that level would be the Ring Nebula. And that's a very faint and also pretty tiny object in the sky. That is around a 9 magnitude. And then out here, you just keep going fainter and fainter. That's where you're talking about the dimmest objects in the universe, some ancient galaxies and so on. So that's not super intuitive. The reason why it operates this way is because early on in astronomy, a lot of the focus was on measuring stellar brightness. That's what astronomers could make sense of at the time. It's like, okay, these are stars in the sky. How are we going to measure them? And they did so in a ranked format. So the brightest stars, you're going to rank as a first magnitude. And then you go second, third, fourth, fifth magnitude, getting dimmer and dimmer down the line. Like a contest, right? So first magnitude would be brightest. And since astronomy is among the oldest of the sciences, that just continued to develop under that same astronomical magnitude system. And so they ended up shifting brighter objects like the sun and the moon and some brighter planets. They ended up shifting into that negative section of our number line. Also interesting about our magnitudes is that if you jump from let's just say from Vega to something that's going to be a bit dimmer than Andromeda out here at a 5, that means this object, like Vega, would be 100 times brighter than this object. So you go in those steps of 5, and you're dealing with jumps of 100 times. So if you've used like a sky app that lets you navigate and see what's out there at a given time in the sky, we'll get to those in a moment. When you click on objects, magnitude is going to be one of those things you see. You'll see it reported, not just as a whole number, usually as a decimal. And that's a measure of brightness. So at least that gives you this context. If you do explore apps like that, it provides that background. This is how we measure that brightness and give it a number in the field of astronomy. Okay. Also kind of cool on that chart is I mentioned Andromeda. I didn't emphasize it too much, though I should. That is an example of a galaxy you can see with your eye. You don't need telescopes or binoculars because it was before that magnitude 6, right? So that's pretty neat. And we'll focus in on Andromeda too. Okay, here we have C is for coordinates. And we're going to deal with two types of coordinates in astronomy. We talk about altitude-azimuth coordinates, and then the next one will be our equatorial coordinates. So altitude-azimuth, we can best compare this one to just how we're thinking of measuring objects using our handy angular measurement tool. If you were to use those same tricks, you're an observer on the ground here. Maybe you have a compass with you to help guide you through the sky. You can do things like measuring, let's say there's an object that's 10 degrees above the horizon. This diagram is showing you the horizon. So you could even just count up and kind of start stacking at arm's length. 10 degrees, 10 degrees, counting up. So your horizon is for altitude is your 0 degree marker. And then as you climb up higher and higher in the sky, right above you is our zenith, and that's our 90 degree marker. So you go 0 to 90, and of course you can do that 360 degrees around. And that's what's going to get marked off by your compass directions. And that 360 degree turn is called our azimuth. So north is just about this corner of the room here. That's roughly true north there. That is a 0 degree marker. And then as we go around, we count up. It's 360 degrees all the way, right? So we go in quarters. We go to the eastern sky, which is in that direction, roughly that corner of the room. That is your 90 degree marker. You point south. Due south is 180 degrees. West is 270 degrees. And then back to true north. So those are your azimuth measurements. So those two things combined, your compass direction and your altitude, give you coordinates in the sky. But that only works for an instant if you're talking about a specific object. Well, the sky's not moving that fast. It'll work over like, set few minutes or so before you start noticing major changes. But yeah, the Earth itself is doing this, right? Earth spins. And because the Earth spins and we're standing on Earth, the sky is going to appear to move as the night goes on. So that means if you're trying to measure something, let's say like around 10 p.m. tonight, with this altitude azimuth system, okay, I'm going to measure it. I've got my compass. I'm measuring. I got the azimuth. I got the altitude. That's my coordinates for that object. In the next hour, it's going to be different. So it doesn't keep up. And that would be something that would be very useful for us as we want to try and map out objects, especially stars, the celestial sphere. We want to map that out, give a given star specific coordinates, and that's where the second system comes in. Equatorial. And if you're familiar at all with telescopes, or you've browsed around online looking at telescopes too, you'll find that the mounts, the tripod setup and the mount the telescope sits on, it'll either be described as altitude azimuth or it'll be described as equatorial. And they both serve different purposes. I can answer questions on that if you have them, but that could be a whole other presentation. So let's just dabble in equatorial here. So this diagram is showing you Earth at the center. And then around it, there's this imaginary celestial sphere. Because of course, every object out in space, the universe is three-dimensional. So every object out there is going to have different set distances, different true distances. But all of those stars, those galaxies, nebulae, star clusters, they're all so far away that we can easily model a system treating them as if they're all the same distance. They're just a spherical image in the sky, and we can start building coordinates from that. So that's what we call our celestial sphere. All right, so then we have this line, the celestial equator, which is if you took our equator on Earth, right, which is on our globe here, coming right through here. If you took that equator, grabbed it, and pulled it out, all at the same rate, you get the celestial equator. All right, so we can even map that on your star apps. We'll come to one called Stellarium later that projects out the celestial equator. And then down here, you have an item known as the ecliptic. And the ecliptic on the celestial sphere maps out the path of the sun throughout the entire year. So the path the sun follows throughout the year. We'll see this too. A lot of this is a little abstract, but we're going to narrow in on how this works. And then you can also send out the North Pole, and you can send out the South Pole and get celestial poles. So it's basically taking the Earth and our almost to the extent of our latitude and longitude lines and branching them out beyond our globe, mapping that all onto our skies. So here's another view of it. I like to show you that simpler view first, because when you look at this, it's like, what's going on? So you can still see similar things here. You can see the celestial equator. And now you see that that equator has been given numbers. Those are our right ascension coordinates. Okay? And then here we have the ecliptic again. You can see the sun tracking around in different seasons, going all the way around once a year along that ecliptic path. You can see constellations mapped out onto this too, showing us our celestial sphere. What you won't see very well depicted on here are the planets. And that's because if we even go back to the original definition of planet, planet means wandering star. So especially over a human lifespan, even several human lifespans, the celestial sphere, all those stars out there, all those constellations, pretty much stay the same. The planets do not. They wander through the constellations. The sun appears to wander through the constellations along that ecliptic. So we can't map out the planets here, and they're not going to keep up with an exact equatorial coordinates. Those we will have to keep track of. But the stars themselves are pretty exact along this system. So that's our right ascension, and then going up, here's our 0 degree marker, similar to altitude. We're going up, and that is our declination. So those are the two coordinates you need for this system. So now what we'll do is we'll jump into Stellarium, not only as just to show you what that even is, but also to dabble in what information you can pull from it based on our ABCs. So I'm not even going to come to this one just yet, if at all. We're going to go to stellarium.org. Stellarium makes you think of planetarium. And that's pretty much what it is. It's your at-home planetarium. It's available for pretty much any platform, as you can see up here. There is an app available on the App Store and Google Play Store. And we're going to use the web-based version that you can use on pretty much any device. Okay. So yeah, this has us set up pretty well for our location. So you would come down here, and it's just telling you, yeah, it's nearby. It's doing its best based on probably the IP address of this device. And that's going to be good enough for us to figure out what's in the sky. Now, it did do some time traveling for us, did jump ahead a little bit. We're going to reset the clock to current time because it's still bright outside. We're heading into summer, and our days are getting longer. But the sun is setting presently. And we'll look due south for now. And we will start heading into the evening sky a little gradually here, just as we get into twilight and stars begin to show up. Okay, so this is heading, let's just get it right to 9:30. Okay, we'll still have some, ooh, there's a fun view. We'll still have some astronomical twilight, meaning the sky's not going to be perfectly dark tonight. What's kind of unfortunate about a night like this is it won't be a perfect dark night, because as the sun sets, tonight, this doesn't happen all the time, but tonight the moon, nearly full moon, will be rising, which means that the moon's going to start giving you some moon glow in the sky, and it'll actually be pretty similar on either sides as the sun sets and then the moon rises. So not the darkest of skies tonight, but that's okay. We will have a window in here where we can perhaps do a little bit of deep sky observing reasonably well. Okay, so yeah, you can see the moon just starting to head towards the horizon on the eastern side of the sky. Because now that we have stars out, let's take a look at this view where we can see a good, almost everything, yeah, everything from eastern horizon to western horizon. And if we start clicking through the time again, notice how the stars appear to move across the sky. Again, all driven by the Earth's rotation. We're spinning, and that's what's driving that motion. But you could see that approximately things eastward will head westward. Things rise in the east and set in the west. That's what the sun does too, right? So when something's in the east, it sets in the west. Things do change a little bit when you head to the northern skies. Well, maybe you can see the Big Dipper there. Right here is the Big Dipper tonight. And then here, a little harder to see, is the Little Dipper. And if I bring up the constellation lines, you can trace those out, and they get labeled and everything for you, so you can figure out what these objects are. Little Dipper is made up of much dimmer stars, as you'll see tonight. It can be challenging to spot. The brightest star of the Little Dipper is the North Star. So I can click on the North Star here, and it does pull up its information. Things like magnitude. Notice its magnitude is a 2. If we can recall the star Vega and where that was on our line, does that mean Polaris is brighter or dimmer than Vega? Dimmer, exactly right. So Polaris is dimmer than one of the brighter stars in the sky, Vega. So that's the North Star, points due north. And I'm going to bring up these grids, because these grids are your coordinates. This first one is your altitude and azimuth. So this is your zenith point, that 90 degrees up. This is your 0 degree altitude on the horizon. And then, like we talked about before, your azimuth goes north, east, south, west, back to north. So that's that system, and you can see it fully mapped out across our sky. It's with respect to the observer, with respect to you looking up in the sky. Now, if I overlay the equatorial, you can see the difference. This kind of brown or orange color is altitude azimuth. The blue is the equatorial. And you can see how the top of our view, that peak declination, drops down towards the North Star. Let's get rid of altitude azimuth. So it just about lines up. And as we said, this is mapping out the celestial sphere. This is another model. If you want to come up and check this out later, you can. The Earth is inside here, so the globe of the Earth, right inside here, it spins. And then out here, this globe is the celestial sphere. So if we start time traveling again, we're already up late. It's already 2 a.m. So we're going to start time traveling, and notice when we're looking in the northern sky, everything is appearing to spin around the North Star. And there's morning. So let's go back to current time and skim through again. Everything's spinning around that North Star. And that means the North Star for us in New York will never rise or set. It's going to stay put. It's out there right now, even in the bright skies. Even in the daytime, and the whole sky will appear to spin around that. But when you look southward, it's the case of things eastward will eventually set westward. All right. So that gives you a baseline. Almost every sky application is going to have grids that you can put on like that to start learning how to pinpoint these objects and what their exact coordinates are. You can see when I'm still clicked on Polaris here, I have both the right ascension and declination for my equatorial, and I have the altitude and azimuth for my altitude and azimuth coordinates. So really useful tool, and we're going to keep coming back to the Stellarium app. So that way I can continue to show you how to use it. And this is, again, just one example of tools that exist out there. And probably the most handy version of these is the one that you'd have on your phone. So we'll talk about those too. All right, we'll dive back into this. So, okay, now we're finally here. We got our ABCs. Let's talk about what's in the sky this summer. First one, and thankfully a really important one for tonight. That ISS is the International Space Station. And here's what it looks like. It's a space station in low Earth orbit. So that means it's going around our planet. And it's orbiting just under 250 miles above the surface of Earth. Which means it is still kind of skimming the atmosphere a bit. And every so often, the ISS has to be boosted. Because if they just left it alone, eventually it would fall out of orbit because of where it is. So that's a very important part of the ISS. But yeah, this space station, keep in mind, it's the size of a football field. It's massive. A lot of that size is due to these huge solar panels that power the craft. It goes around Earth once every 90 minutes, going 17,500 miles per hour around our planet. And I can give you a little bit more sense of, okay, that's a lot. I don't think I've ever gone that fast, though. So at that speed, you could travel from New York City to Los Angeles in 9 minutes. So really zippy flight there. So this is where astronauts have gone for the last couple of decades, primarily. It's been over 50 years now since we've been to the moon, and since then astronauts have been exploring low Earth orbit. And the ISS is like, as of right now, the pinnacle of that exploration. So if you hear about astronauts going into space, this is where they go. Now, what's amazing about the ISS is that you can see it. It's big enough and close enough that we can see it as a point of light going across the sky, almost like a very bright moving star. It's a best way to describe it. And here are some upcoming flyovers for the ISS. You may notice something here. There's a flyover tonight. So tonight, if we're going to look at this magnitude here, we can measure the brightness and estimate the brightness of the ISS during a flyover. The light that we see that looks like a star in the sky is coming from our star. So the sun is shining on the space station, and the solar panels especially are reflecting that light back down towards us. So tonight's flyover is going to be a negative 3.1 magnitude flyover, which puts it at around, Venus and Jupiter, which are really bright objects in the sky. So nice and bright this evening. The start time for this flyover at an altitude of 10 degrees. So that just about, when it's coming in the northwest here, that will just about clear our tree line. So your fist at arm's length, it'll just about clear the tree line. So we should see it just as it makes it to 10 degrees in the northwest. That's at 9:54 p.m. So do keep in mind you'll have to stick around a little bit afterwards to see the ISS. The highest point is going to be 9:57. That's in the north-northeast at 48 degrees. That's a pretty high flyover. And then it will end in the eastern sky at almost 10 p.m. at 22 degrees. Now notice it doesn't make it all the way across the sky. And that's because eventually, just like the sun is now setting for us and we're entering nighttime, and what we call the terminator along the Earth, where the light of the sun meets the dark, the shadow of the Earth itself, the ISS will do that too. It just happens later for the ISS because it's way higher up above us. So eventually it will enter that shadow, and it does so before it hits our horizon on the eastern side. Okay, then tonight there's actually a second flyover. This one might look a little weird though. It is a decently bright one, starting at 11:31 p.m. in the west at an altitude of 10 degrees. It then, within, I don't have the seconds mapped out on here, but it's just under a minute, the tail end of 11:31, I would say. Again, in the western sky, altitude of 14 degrees, and that's where it stops, actually. The highest point is also the end time for this flyover. So this is a short one. This is the one to see tonight, I think. And then tomorrow there'll be another one, a little earlier in the evening, 9:04 p.m. Northwest. Then for start time, 9:07, altitude of 32 degrees, a little bit lower in the sky, and then ending at 9:10. So yeah, well, I think this is, let's try for this one tonight, and we should be able to see it fly over. Now, if you want to explore, it didn't work. Let's just go to heavens above. Heaven. buzz.com. Doesn't like that link, but this worked. This is just one method to look for satellites, and they're just a table. You get a table just like the one I showed you. We got to go over here and make sure our location is set up. So let's see if that's going to work. Yeah, we'll say allow. That's fine. And good. Got our location. And now we're set up for Kopernik. So we can go click ISS, and it will give you a breakdown of all the flyovers coming up.
Can you make that larger?
Oh, yeah. Let's do that. So you can see those three I had labeled so far, but there's actually a good string of them coming up here over the next week. So there's lots of opportunities. And then there's other satellites like the Tiangong Chinese space station, which is also a pretty bright flyover, and it does orbit at a similar altitude around Earth. So again, there's some opportunities here, but they're all morning flyovers. That's not always the case, but at the moment it is. And we have Starlink passes. We'll talk about those. There's Hubble Space Telescope. So you can come and track a whole bunch of these. Well, actually, I think we'll come back to this one too, the 3D orbit display, because it is fascinating, if not a little disheartening. We'll get to that. But that's a great tool, among many others that are out there, to track the ISS. Now, who's on board? There's astronauts on board the ISS tonight. Let's find out. There's a great website. It's called Who is in Space. It tracks all the humans that are out there flying around Earth. And it tells you, this image here is actually a view out of the space station. When the astronauts have free time, this is where a lot of them go. It's called the cupola, and it's the biggest window structure on the ISS that looks right down on Earth. Pretty amazing view. There are 10 humans in space at the moment. And let's scroll down and find out who's out there. So, flying aboard SpaceX, ISS SpaceX Crew 8, which is a NASA mission, but it is a SpaceX rocket and capsule that the astronauts fly aboard. So it's a partnership. This is ultimately, at least on the American side for the ISS, what replaced the space station over here, or space shuttle, excuse me. There's a model of the space shuttle in the room here. It's about 1/15th scale. And that was decommissioned in 2011. But so over that decade, I think 2020 was when we finally started sending humans up. One of our local astronauts, Douglas Hurley, flew that first crew mission, Crew Demo 2. And if you don't know Doug Hurley grew up in Owego. So kind of neat that there's that history. And then he retired, which I think is a good endpoint after all the missions he flew aboard the shuttle to kind of like ignite that next jump into space exploration. So who's there now? We have 4 astronauts, or 3 astronauts, I should say, and 1 cosmonaut. And I want to emphasize here Jeanette Epps. If you don't know, Jeanette Epps is, I guess, semi-local to our region. She grew up in Syracuse. She's on the ISS tonight. And will be for, I can't remember exact end date, but she'll be there for at least another few months. So pretty amazing that we have someone that grew up pretty close to home here, up on the ISS. So they won't see us, but you can wave to the ISS tonight if you want. Wave to Jeanette Epps. Then this is ISS Soyuz, which that's going to, the Soyuz rockets and craft, those are going to be Russian spacecraft. And one cosmonaut I want to emphasize here, how do you pronounce that first one? Sasha, if you can see, how would you pronounce that name? Oh, okay. Yep. Yeah, it probably is pretty tiny on your end. Oleg Kononenko? Okay, so I made my attempt. But yes, he is, he has the record for longest duration in space. If you look here, we'll zoom in a little, 989 days in space. That's the record. He's not leaving the ISS either, like not necessarily anytime soon. He's just going to keep adding up those days. It's pretty incredible if you kind of compare it to other timelines here. This is 251. This is 252. He's been in there for been on the ISS for almost 1,000 days. Do you have a question?
Is that continuous? Like, has he been up there that entire time?
That's continuous. Yeah. So that's just this mission that he's a part of, and clearly a major point of study for how space affects the human body. That's one of the most critical items that they take into account on board the ISS, because that context is going to provide us ideas of what it's like to travel into deeper space, out to long duration missions on the moon, or out to Mars, which is going to be around a 6-month flight there. So pretty amazing. And then we also have the Chinese space station, and there's 3 astronauts aboard that craft. And again, you can see both ISS and Tiangong on heavens above, and you can track both of them. And again, they're similar in brightness most of the time. All right, so that is Who is in Space. Really nice tool. It does change every year. And sometimes there are quite a few astronauts on the ISS when these private missions go up that are called Axiom. Usually adds like 2 to 4 extra astronauts up there. I'm sure it gets a little bit crowded, but they're short duration missions. So doesn't last too long. And maybe it's nice to see some new faces, I don't know, every once in a while. Okay, let's go back here. All right, so we talked about SpaceX with the Crew Dragon missions for the ISS. There's also this system that's purely just on the SpaceX as a company and one of their missions, which is SpaceX Starlink. Perhaps you've heard of Starlink. It is, the goal of it is to provide a global internet system using these satellites scattered in a constellation in orbit around Earth. So every time I have to update this slide, every time I talk about this Starlink at least, because this number changes frequently. I think last time I talked about it, it was at 4,000 satellites. Now it's at 6,000. So they just keep sending up those satellites into orbit. They launch aboard a SpaceX Falcon 9 rocket out of Cape Canaveral. There is the next launch is scheduled to happen pretty soon here on May 27th.
Actually, it happened
a
couple hours ago.
Oh, okay, then it happened.
Yeah, at 2:45 UTC. Actually, I take that back. It was about almost a day ago.
Okay.
And there's actually going to be a very low pass in about 15 minutes.
Oh, what else? This is.
Probably not worth giving it a shot.
Okay. All right, but either way, that's pretty exciting. In the sense that let's take a look at what we can see when Starlink flies over. And there's also this website here. We won't go to it right now, but you can go to findstarlink.com for just as one resource to pinpoint these satellites, much like the ISS. So here's a Starlink pass from May 5th of last year. And there it goes. So you can see, we're talking about magnitude again and brightness. Right here is either they're oriented in a way that they're reflecting more sunlight towards us, or they're just passing through a particular bright part, and they're flaring up there, but you can still see the train of Starlink satellites. And that's how they launch, and they start to spread out in this long train, and eventually find their own locations along the constellation. So they don't stay like this long train. But this was early on in launch, similar to what potentially that flyover would be tonight. Now, I want to emphasize this a little bit with, whoops. If we go back to heavens above and look at the Starlink 3D orbit display, that's not every satellite in orbit around Earth. That's every Starlink satellite in orbit around Earth. So you can see here as you hover around, it's on one hand it's fascinating that SpaceX knows. Of course they should, because it's their assets. But in this huge constellation of satellites, oh yeah, this is Starlink 31823. Sure. It's pretty fascinating on that front. But trouble with these satellites is that they do have kind of a net negative effect on the field of astronomy. They affect data capture. There's just so many out there. It's not to say that even beyond Starlink satellites, those little objects floating out in front of your telescope, in front of your camera, those will show up. And the more you put up out into orbit, the more you're going to see them. And that's certainly something we've noticed here. Not only visually are we seeing more satellites, but primarily in data capture. You'll get these lines streaking across your long exposure photography from satellites like this. So, and here's that example of a train of a recent launch. So, they're interesting to see, but certainly we have complex emotions about Starlink system.
How high are they?
That I don't know off the top of my head. Good question. Drew, do you happen to know how high the Starlink satellites fly at all? I'm curious now, too. All right, let's carry on from this.
291 kilometers. So it's actually lower than the ISS. At least the ones that went up like 24 hours ago.
Okay. Interesting. All right, so now we'll get into the solar system. We talked about near-Earth satellites, human-made objects. Now, objects out in the solar system, natural objects, starting with the sun. Now, a lot of this talk is about night sky objects, and we focused a lot on the sun over the last couple months with the eclipse. But it's not the end of talking about the sun, because there is a solar maximum that, at this point, I think we can pretty much say we're well into. It's estimated to be in the 2024 to 25 period. We really don't know until it starts winding down again on average. So you kind of have to look at it afterwards and see, okay, what does this cycle look like in the end? What is this maximum? And this is when the sun peaks in its activity. For even to narrow its definition down even more, it's when the sun's magnetic field is on the verge of flipping. So north becomes south, south becomes north. And leading up to that flip, things get very chaotic and turbulent across the sun. The magnetic field lines all start twisting together and getting all tangled up, leading to many storms across the sun. And this one was a sunspot region. These spots on the sun are called sunspots. That works well enough for what we need to. That's what they look like, right? They're cooler regions on the sun. Now, don't stand on a sunspot. still super hot, but cooler to their surrounding plasma. So these are representative of where major storms are happening. And ones that are this big really only show up during solar maximum. This sunspot region was visible to us and started forming over the last, probably even a little bit over a month now. And this is what was responsible for the aurora you heard about, was that grouping. Now, it has since rotated away to the other side of the sun, but they are tracking some of the CMEs that come out from that side. They can get an idea of what the conditions are on that side of the sun based on observations from a couple different solar telescopes. And they are seeing storms popping off again on that side. So most likely it will survive in some form. Whether it's bigger or smaller, hard to say, but we might see it swing back around pretty soon here. So we'll talk more about the aurora in just a moment, but yeah, lots of storms happening on regions like that. Now, I want to emphasize, of course, do not view the sun without the right equipment. If you don't know how to observe the sun, just don't do it. Come to a place like Kopernik when we're doing solar observations, or any observatory, or look online at some recent images of the sun. It's going to be, those are the safest ways to enjoy our star. But we can see the effects of solar maximum. So I do want to show you a couple views here from, I think this is from Solar Dynamics Observatory. And, oh, these were animated, but now they don't want to play. That's too bad. Let's try clicking ahead one more time. Nope. Okay. Well, anyways, during the total solar eclipse, one of the big things that you see is, oh, there it goes. When the moon covers up the sun is the solar corona. Now, there are solar telescopes out there in space that have what it's called a coronagraph, and you basically block out the sun so you can see some of the corona, making almost an artificial eclipse. So that's what they're tracking here, and they do this every single day. They're watching the sun and the corona to pay attention to those. Now, this is happening. It's like May 20th to May 24th is where this data is from. And it's a time lapse, right? So this is sped up. And you see these bursts of material shooting out from the sun. Those are coronal mass ejections. And when that happens, it's actual material from the sun getting sent out. So it's effectively like if you've seen solar flares before, these arcs across the sun. This is when they get so strong that they disconnect and chuck a whole bunch of material out into space. And when those are aimed towards Earth, that's when we get hit by the solar wind. And that's when we get the northern lights. It's when that solar wind, those solar particles interact with our atmosphere, ionizing it, and producing some wonderful displays. Now, this image here is at Kopernik. This was taken this year on May 12th. This is not going to be as dramatic as the wonderful images you saw across the social media and so forth that day. May 12th is when this storm system was winding down from that big sunspot, and so the northern lights were waning. This is our northwestern sky here. Here's the main building. This is where you are in here in space science. And yeah, you can see some of this high altitude aurora. Now that wasn't, I didn't see it with my eye. I was tracking that area of the sky with my camera with long exposures and started to notice color showing up. Now the auroral displays on That would have been May 10th and 11th. Those evenings where, yeah, it was cloudy here. Those would be visible to the eye, for sure. And maybe the images that you saw certainly had an effect, like that were going to be more vibrant than what your eye would see. Time lapses would make it more dynamic and dramatic in its motion. So there is a little bit of incongruity there with what you could expect for your eyes to pick up. But you would see it with your eyes with storms of that scale. So I have a little time lapse here too. Oh, it's just taking some time for these to load up, I guess. Let's go back. Doesn't want to play. We'll just let it sit on it for a second. There it goes. So this is going to be looped. And it's also going to show you that there was that moment of aurora, and then clouds rolled in, and then it stayed cloudy that night. So it was fascinating too, because the Kopernik Astronomical Society, which is something that if you're interested in astronomy, it's basically our astronomy club, maybe something that you want to check out or join. And there's a whole bunch of society members here tonight if you want to chat with them. But we have a whole Discord that we chat with each other with, and at first it didn't seem super promising that they were going to show up, but then it was like this footage came from a 360 camera tracking the entire sky at once, and based on the timeline for that footage, it was pretty much just this 5-minute window around 10:50 p.m. that we could spot these northern lights in camera view. So it was pretty brief. A brief moment today showed up here in our skies, but you can see how they kind of wave across the sky in this time lapse. You can see some of that pillaring in the sky. So pretty amazing. And we're happy to at least caught this, even though at that point they were waning. And thankfully, it may not even be exact solar peak right now. Peak may be ahead of us, and even on either side of solar maximum, there are more opportunities to see aurora come further south. Now, this particular geomagnetic storm was a G5 class, meaning it was significant, and G5 class storms also have the chance to cause damage to things like satellites or our electrical grid. Back in 2003, that blackout was caused by solar weather during around that maximum. So from all I've heard, there were some localized blackouts and issues, but it seems like we survived that G5 class storm. And it just put on a wonderful display for us. So it's kind of like a mixed bag of, I really want to see aurora, but also I kind of like my power. So there should be other opportunities, though. We don't even, here in New York, we don't necessarily even need a storm of that magnitude. That storm down in Florida, people were seeing and able to pick up the aurora in their cameras. So that far south, they were spotting them. So even, let's take a G4 class storm. We'll take that. There should be more, and we'll see what happens with that sunspot too, that region that comes back around. If you want to explore resources related to the aurora, once the video starts playing, it really doesn't want to move on from it. Okay. So some solar and auroral resources. Try and say that 5 times in a row. So this website here for the Solar Dynamics Observatory, we'll click on that. This gives you some very recent views. This is called the sun now, so it's the most recent image today from the Solar Dynamics Observatory, and you can look at it in all sorts of wavelengths and views. There's a pretty reasonably sized sunspot region. By the way, that big sunspot group that we showed you before, 15 Earths across in size. Give you a sense of scale. So yeah, if that group does come back around, it'll come back around over here when it as the sun rotates. So Solar Dynamics Observatory is a great place to get some recent data. There's all sorts of galleries you can view here. And then spaceweather.com is a great website for a nice summary on the geomagnetic storms. They usually list them right at the top. Here is what's going on and your prospects of seeing aurora. You can come down here too and get a probability view of where the aurora might show up. So you can see this is mapping out the possibility of seeing aurora at a given location, not quite reaching far enough south for us this evening. But that's the kind of tracking that you can do here. Okay. Now let's jump back in here. So that's the aurora. We're going to speed things up a little bit here. So the moon is going to be visible later on this evening. It won't get above our tree line probably until maybe 10:30 or 11. But it does tell you one lunar cycle is 29.5 days. That means you can see all the phases of the moon in that time. Right now we're just past full moon. And the best way to observe it is with the unaided eye, with binoculars, telescopes, and cameras. So we're pretty familiar with the moon, right? Let's carry on and go to our planets, or should I say planet, at least in terms of convenience, meaning timing of day. Saturn is going to be the primary planet available in the evening hours this summer. It's going to get better and better as you head deeper into summer. And this is the great ringed planet, right? So you'll see the main planet itself and the rings too, although I will say they won't be as face-on as this image. This is an image taken through our 6-inch telescope at Kopernik. The rings are starting to go more edge-on, and when they do that, they become a little less visible. So keep that in mind too, but it's still a tremendous object to look at. But that's not the whole story. If we jump into Stellarium quick, this is tonight, and you can see in late spring here, here's Saturn, but it was showing it there. Here's Saturn below the horizon. This is at almost 11:30 p.m. tonight. That's where Stellarium currently is. So right now, you would have to stay up or set your alarm for just after 3 a.m. to see Saturn in the sky. But watch this. If we go back, let's say to 10:30, and we click ahead by the months here. We're in May right now. Let's go to June, and then July, and then in August, Saturn is finally out there around 10:30. So we're looking more later summer for Saturn to be nice and high in the sky at a convenient hour. But if you're willing to stay up, even tonight, you could see Saturn out there. If we go back to current date, and we take a look at the morning hours, that's where the story is a little bit different. We'll go to the morning hours tomorrow morning. Ooh, it's getting bright. I'm going to turn off the atmosphere because the sun is starting to block everything out as it's starting to rise, and we want to see exactly what's out here. So Mercury, Mars, Saturn, just before sunrise are out there in the sky. Even down here, Jupiter, if we click ahead a little more, There actually was just a conjunction of Venus and Jupiter, but look how close they are to the sun. You really can't observe that. Definitely can't observe it very safely, and even still, it's when you're dealing with objects that close to the sun and with the sky all brightened up like that, it's really challenging and dangerous, as I said. So Venus and Jupiter are there at the sun right now. You may have heard of a planetary alignment of sorts coming up around June 3rd. They're kind of already lined up right now. And in the end, really, if you were up early in the morning, pretty much with a good horizon, you can see Mercury, Mars, and Saturn with the eye. So yeah, the planets are a little more of a challenge, especially here at Kopernik. We're open Friday evenings. So later summer, we'll be able to observe Saturn. Okay, jumping back here. There's also the Perseid meteor shower coming up in August. It peaks August 13th, but there's a good week on either side of that where you can see quite a few Perseids. And the best way to observe Perseid meteor showers, get to a dark sky location. We get a good showing of Perseids just about every year as long as the moon's not in our way, which that's something I forgot to check, and we can do so quick. And best Perseid meteor showers, sometimes you can push 100 meteors per hour. Usually I would say when I've observed it, I might be able to count 30 if I'm standing there looking in an approximate northeastern area of the sky. But it can peak as high as that. This is the wrong stellarium. Okay, let's go northeastern sky, and we're going to skip to August 13th. Look how easy it is to just bounce around through time. All right, northeastern, and we're a little bit, oh, that's why, yeah, we're still morning hours. There we go. So heading around midnight, after midnight is ideal for observing the Perseid meteor shower because you'll be looking for the constellation Perseus, which is where a lot of these meteors will originate from. And as that gets higher and higher in the sky, your probability increases to see those meteors. So it's in this location of the sky, but you can really see them anywhere. They're just all going to appear to originate from that constellation. So that's August 13th and a week there before or after. My favorite meteor shower. It's a really good one. Oh, and I forgot to check the moon situation quick. Well, let's see how we're doing. Oh, I don't see it. The moon can affect your visibility of meteor showers. And there's Jupiter. But yeah, let's do a quick, here's a look at the, hang on. Oh, there it is. Let's do a quick search for the moon. Oh, it's a good year for the Perseid meteor shower. No moon. Excellent. So keep that in mind too. All right. We did that. The Milky Way is another phenomenal object. This is the Milky Way at Kopernik through a camera, a long exposure shot, mind you. But your eyes do see the Milky Way. The Milky Way is our galaxy. It's the galaxy we live within. And we can see in the summertime the core of the Milky Way galaxy, which is especially bright. It hangs out right on our southern horizon where the skies are really dark. And even in this image, at least at the time, Jupiter and Saturn were out. This was a couple years ago. But yeah, really nice band, and you can usually follow that band across the sky. Deep sky objects. This is actually within and around that core of the Milky Way. We have some nebula. You're going to find a lot of nebulous regions, like Trifid, the Trifid Nebula M20. And the Lagoon Nebula M8. So this is labeled for you here. You even have some star clusters as well. But the Lagoon Nebula a bigger nebula here than our Trifid. These are both star-forming regions. So where some stars are born out in our galaxy. This one is particularly active. You can see just how many stars are clustered in here. That pink coloring is coming from hydrogen. It's actually energized hydrogen. So the hydrogen there is emitting light. And then the bluer colors you're seeing here is stellar reflectance. You're getting starlight shining on all these clouds of dust and gas out there, and it's reflecting off, and we end up seeing that as a bluer color. So this is glowing, this is reflecting. And a really lovely contrast. Trifid is an amazing object to image. And so, and Lagoon is, all these are, nebulae are fantastic, and you can get a lot of coloring out of them, just with some simple long exposures even. And then if you start playing with filters, then you really can have some fun. So these are just catalog numbers, by the way, for deep sky objects. The M stands for Messier. Charles Messier was an astronomer. He was, in many ways, a comet hunter. These were his not comets catalog. He didn't necessarily know exactly what they were. A little early to know exactly what nebulae and galaxies were, but he put together this whole catalog of these objects that were not comets, but very interesting. And how we know, for example, the nebulae are star-forming regions. Here's an image of the Dumbbell Nebula. We have another picture of this in the computer lab that you can check out. M27. You can see kind of that dumbbell shape to it, or almost an hourglass shape. A lot of these planetary nebulas are going to take on more of a circular view. And this is not where stars are born. This is where a star has died. It's actually representative of what our sun will do 5 billion years from now and what it will leave behind. The Pinwheel Galaxy, M101. We have an amazing picture of this too down the long hallway. M101 with the supernova from last year that you can check out. This one does not have the supernova, that was beforehand. But you can see this galaxy, which is out tonight, takes on that pinwheel shape. You can almost imagine it twirling, right? The Whirlpool Galaxy, M51. One of my favorite galaxies to observe through a telescope, because that structure, even though this is kind of a dimmer object, especially compared to a closer one like Andromeda, you can really see that structure if you let your eyes adjust to the night sky. If it's a super dark night, you can see the two galaxies, the bigger one and the smaller one. This is in a cosmic collision. So galactic collision here. And you can get these spiral arms and this contrast between those arms, the bright cores. Pretty incredible to both visually see, and then these are all obviously images from a long exposure camera shot. There's the Andromeda Galaxy over Kopernik to give you a sense of what your eyes will kind of pick up when you're seeing it in the sky. Your eyes kind of get the sense of, okay, there's some kind of ghostly object there in the constellation Andromeda. And then as it goes out, it gets dimmer and dimmer. So it's actually in its true scale. This is an object that's a few moons across in the sky. So if we could see it all with our eye, which unfortunately we can't, it'd fill up a good little portion of that sky there. So we've learned a lot about Stellarium. We are going to skip this one and just close out with some tools that you can use. Stellarium, you can download it at stellarium.org. You can use web-based versions. You can go to the app stores and download it there. There are some other stargazing apps, though, just as a few examples. There's so many. I didn't list them all here, but Starwalk, Skyguide, those are very similar in how they work. They're good beginner stargazing apps. Sky Safari is where you start to get more advanced. You'll find that one, these ones have free versions. Sky Safari has different levels, and at the highest level, you'll have to pay a little bit to get that one. But it's when you're really starting to delve into the hobby, and maybe you have a telescope, you have some camera equipment, fantastic app for that use case. And you can even control your telescope using Sky Safari with the right equipment. So very useful app. All of them useful. And lastly, your smartphone. So your smartphone has become, even in the last couple of years, a pretty nice astrophotography device just for dabbling in that hobby a little. The reason why I think this aurora situation became such a phenomenon is because the camera we have on us all the time has become pretty decent at even just handheld long exposure shots. A lot over the last couple of years, both Google and Apple, they've come out with night mode that can take several pictures at different exposures and stack them all together in the span of 10 to 30 seconds. And when you do that, you're able to get some decent things. So just handheld, this shot here, I think was around that 10-second exposure marker. And I was taking pictures of the sky at that time with my phone to help inform and frame up my larger camera that I got the aurora shot from. Can you see this pink in the sky here? It was very faint that night, but even my phone was able to capture that. And I bet your phone can too with that night mode. So that's part of the reason why that became such a phenomenon. It's because everyone was able to take pictures of the aurora and capture some of that vibrant detail. So incredible how accessible that technology has become. You don't need a super expensive, separate, dedicated camera. You can just use the camera you have on you. And then over here, this is also handheld with the telephoto lens on my camera. So if you have a telephoto lens that can zoom in even more optically, not digitally, not just pinch to zoom, right? You gotta have an optical lens to push that magnification. You can capture the moon. And as long as you knock the exposure down enough, you get some pretty nice detail. Okay, so your smartphone, fantastic tool as well, not just for stargazing apps, but also imaging. And with that said, I'm so happy this slide works this time. So I had the extra emphatical there, extra exclamation, because we have clear skies tonight. And we also have that space station flyover very shortly. So to that end, do we have any questions in the live chat? You can check it out quick. Yeah, I'll skip that one. Are there any questions out here in the audience before we depart? All right, so I do have some star maps for you. If you have your stargazing apps, that could be handy tonight as well. We'll give you some sky tours, some star tours with our laser pointer outside too. But if you want to pick up a star map to take home, it gives you a nice breakdown of even more than what I talked about tonight. Otherwise, we're going to start bringing you outside, and at around 9:50, we'll make sure we're all out front to observe the space station. So thanks for tuning into my talk, and we'll have those clear skies.
We also have a couple of our telescopes that'll also be opened, both scopes that are in the yard as well as scopes in the domes themselves. And we have a rule here that you can't leave Kopernik until you actually look through a telescope. So if you just leave your keys up here, then after you're done, you can come pick them up. Anyway, I did take a quick look out there. The Starlink train was not visible, but that Heavens Above website will show you, where it is and when you put in your longitude, latitude, and it'll tell you. Or actually, sometimes I think you can even pick the city you're going to be in. So another great resource. Next week we have a talk about science and religion, and are they conflicting? Are they conciliatory? And Actually, Dr. Tom O'Brien, who teaches at Binghamton University, will walk through that. And so anyway, please avail yourself of the scopes, and we'll look forward to seeing you soon.